Welcome back, everybody, to the next lesson in the astronomy unit. Today we're going to be looking at the planet chart in your reference tables. We're going to move through that. We're going to learn about ellipses, how to calculate eccentricity. You're going to be doing a lab on this. And let's get moving. Got a lot to do today. First off, planetary motions. It's kind of interesting to think about the big picture here. The Earth and all the planets are orbiting around our sun in our solar system, while our solar system is actually orbiting around the center core of the Milky Way galaxy. And it takes about 225 million years, roughly, for our solar system to go around the center of the Milky Way. We're out there on the Orion arm. We are here. And if we look at Sagittarius at nighttime, the constellation Sagittarius, we're kind of looking towards the core of our galaxy. And there's other arms as well, which we talked about in a different lesson. So each column on the page in your reference tables that has the solar system data is important to understand. First, mean distance from the sun. That means the average distance from the sun. It's measured in million kilometers. You notice the moon isn't measured from the sun. It's from the Earth. So just be aware of that. That's one difference. The period of revolution. It's measured either in days, D, or Y for years. And that's how long it takes for the object, the planet, to go around the sun or the moon to go around the Earth. Period of rotation at the equator, how long it takes to rotate once. And that is measured in Earth days. One Earth day, of course, 23 hours, 56 minutes, and 4 seconds. Not quite 24 hours. Or eccentricity of orbit. And this is something we're going to get to towards the end of this lesson, but it's essentially the shape of the orbit of a planet. Planet orbits have shapes. They're not circular. Equatorial diameter, that's how far across the planet is from one side to the other, right through the equator. It's measured in kilometers compared to the sun. You see the sun's very large compared to the rest. Mass, Earth being 1. So these aren't the actual masses in like kilograms, for instance. This is, compared to Earth, how many Earths are these other objects. And you can see some are a lot less than Earth and some are way more than Earth. And density, this is simply, how dense. How much mass divided by how much volume is in each object. And some are very dense, like the Earth, and others are much less dense. When I mention the mean distance from the, just remember, mean means average in this case. You'll learn about it in math class, mean, median, and mode. But the average distance, because we're going to study the shapes of the orbits coming up real soon, but the shape isn't circular. So the different distances that a planet gets to from the sun, if you average those, that's the mean distance. All right, let's focus our attention to the first two columns, mean distance from the sun in millions of kilometers and the period of revolution around the sun in days or years. And I want you to look for any patterns. Now, if we look in the first column, we'll see that as we work down the planets, as we get farther away, not including the moon, you'll notice that the time it takes, or the distance as you get farther away from the sun increases, which is obvious. But if you look at period of revolution, you'll see that the period of revolution also increases, not including the moon. And so they have a direct relationship. As distance increases from the sun, the period of revolution increases. And that should make sense because the farther away you get, the longer it's going to take to go around. It's also actually true that the planets that are farther away physically move slower in their orbits around the sun. And that's simply because they're not attracted as strongly to the sun's gravity because they're not as close. And we'll get into that when we study orbits more in depth. Okay, our period of revolution. This is a really cool applet. I'm sure some of you might have seen this if your teacher has this. And it shows 24 different red lines starting at the North Pole, working their way out towards the equator. And these represent 15 degrees of longitude, each of them. So there's 360 total degrees. There's 24 of these lines. And our period of rotation, if you remember back to Unit 1, the Earth's speed of rotation was 15 degrees per hour. And this is just a good review of that. Each line takes an hour to go across. You can see it, 6 a.m. I can't draw on this, but you can see the mark at least. 6 a.m., this would be 7, 8, and so on and so forth. But our period of rotation, once again, is just how long it takes to spin around once. And it's almost 24 hours. Okay, all planets rotate. However, their period of rotation can vary greatly from one planet to the next. Venus, really, really slow rotating planet. 243 Earth days for Venus to rotate once. So that planet's just getting cooked on one side as it slowly rotates. Jupiter, on the other hand, is a really fast rotating planet. 9 hours, 50 minutes, and 30 seconds for this giant planet to spin once. I already mentioned that's why it has a great Coriolis effect. So they vary greatly. Even the moon's rotation's on there, but we'll get to that later on at the end of this unit. All right, revolution. Here we see the Earth revolving around the sun. Now, this is one misconception that all of you guys make, it seems like, every year, and that's the difference between rotation and revolution. You've got to get this right. Revolution is an orbit around something else, in this case, us around the sun. Rotation is what the Earth's doing as it's orbiting, and you can see it in that applet. It's spinning around its polar axis. That's rotation. So revolution is an orbit, rotation is spinning. And all planets orbit the sun. They all revolve, and their period of revolution increases with the distance from the sun. We already talked about that. Now, there's a formula that you used to have to know in Earth science for this, and it's the period squared. The period of revolution squared is equal to the mean radius, the average radius of the planet's orbit cubed. And so what's neat about this is if you know the radius of a planet's orbit, you know the distance, the average distance of a planet's orbit, you can actually find how long it takes to go around the sun. Or vice versa, if you know how long it takes to go around the sun through long observational periods, think of the old days with Galileo, then you can find out how far away it is from the sun. So both pretty cool things to know. And once again, note that the period increases with distance. All right, let's move on to some other factors, some other pieces of data in that chart in your reference tables. Diameter, mass, density. Make sure you understand what each column means. The equatorial diameter, how far across it is through the equator of each object. And you might be asked questions which make you do a little bit of math. And you have to be able to figure this stuff out. There's no formulas for this stuff. How many times larger is the diameter of Earth compared to Mars? So how many times larger is this number compared to this number? And you just divide them and you get an answer. And it's almost 2 times larger. But you can get the exact number if you had a calculator. Okay, second, what percent are all the planets' masses when compared to the mass of the sun? So you might be asked a question in the mass column, and that's a what percent problem, and I know your math teachers teach you that is over of equals x over 100. And so, you'd be adding all these up and figuring out what percent are those compared to the sun. So it'd be these numbers over this number equals x over 100. And you could figure that out quite easily. But once again, there's no formula for that. You just have to use your brains. Okay, the third one, density. You might be asked a question like, what planet could float in water? And if you remember back to your front page of your reference tables, the density of water is 1 at 4 degrees Celsius. And there's only one planet here that could actually float in water. And that is Saturn. Interestingly enough, its density is only 0.7. So if you had a big, 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 big bathtub, Saturn could float in it. All right, eccentricity of orbit. Now I've been saving this for last here because eccentricity involves a little more thought and some math and some understanding of different shapes. Eccentricity, the numbers, if you look here, are not in any kind of order. 0.206, 0.007, 0.017, 0.093. As you get farther away from the sun, they don't constantly increase, they don't constantly decrease. They're kind of random. All right, let's take a look at a planet orbiting a star and see what an eccentric orbit looks like. Whoops. Let's see if we can get that to work. There we go. Try that again. One more time. There we go. Now you notice this planet speeds up as it gets closer to the sun or its star, and then it slows down as it moves farther away. And this has to do with gravitational attraction. When it gets closer, it's pulling more strongly, both of them on each other. And so to counteract that, it has to speed up its orbital velocity. And then when it gets farther away, there's less gravitational pull between the two, and so it slows down. Now, this shape is not a circle, it's not an oval, it's an ellipse, which is the shape of all planets going around their stars, or our planets going around our sun. Even comets, asteroids, moons, they all revolve in ellipses around their objects that they orbit. And ellipses don't have one center like a circle, they have two centers, and they're called foci. So we can kind of make a diagram of our orbit around the sun, and this is not drawn to scale at all, but the sun would be one focus point of these foci. There's an empty focus point at the other balance point of the planet going around the sun, and there's nothing there. There's no sign in space saying, oh, you have reached focus point 1. It's just a balance point. And there's the planet and the elliptical shaped orbit. And the line drawn through the foci, extending from one edge of the elliptical orbit to the other, is called the major axis. And it's the longest line you could draw across this ellipse, and it always goes through the foci. And that's important for the formula we're going to learn in the next slide. And I know this is kind of cheesy here, but it's the best I can do with PowerPoint. You can see that planet there orbiting around the sun, coming back, and it's going through one orbit in its ellipse. Now, to calculate the shape of an ellipse, we use eccentricity. And it's a measure of the ellipse's, I like to call it roundness. And we're going to be drawing ellipses like this person here with the pencil in lab class. We're going to be using loops of string instead of just pinned down string. And you'll get pretty good at drawing them. They're kind of fun. As far as the differences in eccentricity goes, the maximum eccentricity that an ellipse can have is 1. And we'll see why in a moment, but that really doesn't happen with planets, or else they'd be ping-ponging back and forth between the two foci. The minimum eccentricity a planet could have is 0. 0 is a perfect circle, and planets don't have that either. At least I don't know of any. And an eccentricity of 0.5 would look something like the shape in between. So one way I like to remember it is a maximum eccentricity is a straight line, and a straight line is how you draw a 1. And it's just a quick way to remember it. And a 0 is the minimum eccentricity, and it's a circle shape, which is like a 0. Maybe it'll help you. All right, in your reference tables on the front cover, in the equations box, eccentricity is the distance between the foci divided by the length of the major axis. And in this drawing, you'll see that 60 millimeters is the focal distance, the distance between the foci, between the sun and the balance point. 60 millimeters. You'll see that the length of the major axis is 90 millimeters, and that's this distance, 90 millimeters. And so the way you calculate eccentricity is simply you divide them. And if you look over on the left-hand side, when you divide, the units cancel. And you get an answer with no units, which is unusual because I'm always bugging you to put units on everything. So you get away with it without putting any units on eccentricity. And we're going to practice a bunch of these for classwork and homework, so you get used to it. All right, moving right along. Now, along with these lines with elliptical orbits, let's just focus on the Earth going around the sun for a moment. And we have an elliptical orbit. Our closest point and our farthest point away from the sun occur on dates that I don't think you have to know anymore, but it's just interesting. The 4th of July is usually around the time when we are at aphelion, or the point when Earth is farthest away, and that's the way I like to remember it, aphelion, away. And it's a celebration for us here in the United States, so it's an easy way to remember it. We're at 152 million kilometers away from the sun, so the sun looks a little smaller. And in January, beginning of January, around the 3rd or so, we are at perihelion. Perihelion is when we're closest, and it's about 147 million kilometers. So there's about a 5 million kilometer difference between aphelion and perihelion. And just remember, we are closest to the sun in our northern hemisphere winter, and we're farthest away in our summer. You guys know that distance does not cause our seasons. In fact, we can even take a look at what the sun looks like at aphelion and perihelion. Let's take a brief look. There's aphelion, perihelion, aphelion, perihelion. You get the idea. Away, close, away, close. So the sun does change its actual apparent diameter. Now, how do planets maintain their orbits without flying off into space? We know that the Earth is moving around the sun pretty fast, so it has inertia. An object in motion tends to stay in motion unless acted upon by another force, and Earth is acted upon by another force, and that's the sun's gravity. So the gravitational attraction between the Earth and the sun, because they both have gravity, the sun just has a lot more, is holding the Earth in orbit because it's exactly balancing the inertia force. So when the forces are equal, the planet makes a nice curve, as you can see in this diagram right here, and it kind of follows this path, the actual orbit. If the Earth were to speed up somehow, it would move into a farther, more distant orbit. If it were to slow down somehow, it would move in a little closer to the sun, but they're always balanced. We can take a quick look at something like that. Hopefully this will work. Some of my links don't always work when I want them to. And I don't think oh, nope, I'm not going to get that one to work. All right, let's finish off the lesson here with, I like to just show this. I know it's kind of cheesy, but one way to think about gravity is looking at the fabric of space-time. And the fabric of space-time there we go. The fabric of space-time is distorted by objects with big masses. So in this diagram, this massive object on the left that that's pointing to creates a disturbance in the fabric. And I know this is going to be cheesy, but you'll see it. As the objects fall into these depressions in the space-time fabric, they fall towards the object. And in this case, you saw it kind of came in and went around, came back out again. There we go. One more time. And so you can think about that, like planets going around the sun or moons going around planets. They're kind of falling in towards those objects because the space-time's distorted. And I know this is not the best way to show it, but it's okay. All right, hopefully you guys learned something about the planets.